This video will cover part 2 of Pre-Calc 2.6 notes. If you remember from part 1, we left off talking about graphing rational expressions or rational functions, where you have a polynomial divided by a polynomial, in this case polynomial divided by binomial. And we talked about in order for us to graph it, we wanted to find horizontal and vertical asymptotes. So remember, to find the vertical asymptote, set your denominator equal to 0. You'd end up getting x equals positive 1. So let's get out our highlighter at x equals positive 1. Let's draw our vertical asymptote. Then we talked about how we find the horizontal asymptote. We look at the degree of the numerator. So the degree of the numerator is 2, or the degree of the denominator is 1. So when the denominator is less than the numerator, that's when you are going to have a slant asymptote. And it's called a slant asymptote because it's not a horizontal line. As we look over here at the graph, I've already put this in the graphing calculator, you can see that the vertical asymptote is right there, but then the slant asymptote is more of a line that looks like this. So I have to come up with, how do I graph that line? That's what the slant asymptote is. It's called slant asymptote because it's on a slant. And the way we're going to do that is we're going to use synthetic division. So if I'm going to use synthetic division, I'm going to divide this, obviously the denominator, into my numerator. I'm going to put a positive 1 out here, because that's what I would get when I set this equal to 0. And I'll list out my coefficients, 1, 1, and negative 3. And so then I start by dropping down the first 1, multiply, I get 1, add, I get 2, multiply, I get 2, add, I get negative 1. And really all I care about is the part minus the remainder. I don't really care about the remainder part. So this is going to give me the equation for my slant asymptote. If this was a degree 2, that means this has to be degree 1. So this is going to be 1x plus 2. Again, I don't care for this about my remainder. That's not going to be part of the equation for the line. The answer that I get using synthetic division is going to be my answer. So it's going to be y equals x plus 2. So let's graph that line. So if I graph that line, I go up 2, and I do a slope up 1 over 1, up 1 over 1. And that is going to be the equation, or excuse me, the graph of my slant asymptote. I'm just going to go over that with a highlighter so I know that that's not actually part of my graph, but that is my asymptote. So now I have my two asymptotes on here, and I can continue to make my graph by coming up with what values I should put in my table. So if my vertical asymptote here was at 1, then I pick values bigger than 1 and less than 1. So bigger than 1 would be 2, 3, 4, and 5. Less than 1 would be 0, negative 1, negative 2, and negative 3. So I've already calculated these values. So I'd get 3, 4.5, 5.6, 6.75. Over here I'd get 3, 1.5, 1/3, which is 0.3, and negative 0.75. So if I take the time to plot these, 2, 3 would be here. 3, 4.5. Notice I'm getting really close to my asymptote, but I'm not going to touch it. 5.6 and 6.75. That's actually going to be off of my graph here, so I'm not going to take the time to plot that one. So my one branch is going to look like this, which we can see from the graphing calculator. It matches up like that. My other branch, if I go to 0, 3, be right up here. Negative 1, 1.5. Right here, really close to the line. And again, I'm getting really close to this line each time. And I didn't really make this line. I'm a little bit off with my line, because this should really be negative 3, negative 0.75, which should be down here. So I can see that my line was off a little bit when I graphed it. So you want to try to make that slant asymptote as accurate as you can. And again, I'm off a little bit, but that's okay for the sake of what we're doing. but my graph is going to look like that, the other branch. And you'll notice again that that's what my branch looks like here. So when you have a slant asymptote, when the denominator is less than the numerator, the degree of that is, I should say, then you have to use synthetic division. You could use long division if you want, but synthetic division is much easier. And you're only taking the answer without the remainder. So the answer minus the remainder is what you're dealing with. And so this equation here, x plus 2, is the equation for that line. Again, it's called a slant asymptote because it's not horizontal, it's on a slant. Okay, for our next example, this time notice that I don't necessarily have a rational function. I have a fraction that I'm adding another, just a 1 to, so a constant to. In order for me to graph this, what I need to do is actually do this. I need to add these together. Easiest way for me to add these together is to change this 1 to x minus 3 over x minus 3. And the reason I'm choosing to do x minus 3 over x minus 3 is that that's what my denominator is. So now I can actually add these together. I know this is going to be a fraction. If I add fractions, they have the same denominator, so it would be over x minus 3. If I do 1 plus a negative 3, I'm going to get a negative 2, so this would be x minus 2. So when you don't have just the rational function where you have polynomial over polynomial, you have got a constant you're adding to it, you need to combine those and add those together. So you notice that I've already have the graph up here. So we can confirm as we're graphing this that we're getting the right answer. Let's find our vertical asymptote. The denominator was x minus 3, so when I set that equal to 0, I'd have to add 3. I get a positive 3. Horizontal asymptote, compare the degrees of the numerator and the denominator. Well, this is degree 1. This is also degree 1. So when the denominator is equal to the numerator in terms of the degrees, we have to take the leading coefficients and write them as a fraction. So in this case, I've got 1s for both of these. So I'm going to do 1 over 1. Actually, I'm going to do y equals 1 over 1. And I'm going to get the equation as y equals 1 for the horizontal asymptote. Again, if you're confused about how I got this, this is the formulas for that is on the very front side of your notes, and that's something we talked about in the last video. So let's plot these vertical and horizontal asymptotes. X equals 3 is here, and y equals 1 would be here. So I've graphed those. That's going to help me keep in my mind straight what I need to use for my x values in the table. So if this was at 3, I'm going to pick values bigger and smaller than 3. So bigger would be 4, 5, 6, 7. Less would be 2, 1, 0, negative 1. So again, I've already taken the time to figure this out, and you can use your graphing calculator to fill the tables in for you. You don't necessarily have to compute this all by hand. So I'm going to get 2, 1.5, 1.3, 1.25, 0, half, or 0.5, 0.66, and 0.75. So if I plot these, start at 4, 2, 5, 1.5, and you'll notice that I'm just keep getting closer. I notice that my graph doesn't go over to 7, so I'm not going to be able to plot that. But again, I want to make this branch approach the asymptote but not touch. And you notice that that's what I've got over here, is that branch. And then when we graph the other one, 2, 0, 1.5, 0.66. Again, I'm getting closer and closer to this, but not touching. So that'd be this branch. And again, you can see that that's this branch over here in on the graphing calculator. So I've got my graph. And again, with a problem like this, the hardest part about it, I think, is doing this first part, which is coming up with how to combine a fraction with a non-fraction. Okay, for our next example, you'll notice that it says a utility company burns coal to generate electricity. The cost in C of removing a p% of the smokestack pollutants is given by this equation right here. And they're saying that P is from 0 to 100. Obviously, that makes sense. You're removing from 0 to 100% of the pollutants. So take the time to put this in your graphing calculator. You'll notice when you do that, let me just clear these out of here so you're not confused by that. Plug it in like this. 80,000 x divided by 100 minus x. Make sure you put those in their own sets of parentheses. And then you're going to need to change your scale. So go over here to your window and change your window to the settings that I have here. So I invite you to pause the video and get your graphing calculator set up the way that it needs to be able to do this. Okay, so I've already done that. So if I go back to the graph, my graph is going to look like this. Now the question is saying, you are a member of the state legislature considering a law that would require utility companies to remove 90% of the pollutants from their smokestacks. Right now, they only have to remove 85%. The question is, if you're going to apply this law, you're going to want to know how much it's going to cost the companies to meet these new regulations. So let's figure out what it would cost the company right now to remove 85%. So the way that I can do that in the graphing calculator is I can hit this second calculate button. When I do that, I'm going to get this value. So if I hit enter, I can type into here then, when x is 85, figure out what y is. And it's telling me then that it's going to be $453,333.33 is what it's going to cost. So in a minute, I'll fill that in on the blank here. What is it going to cost if I increase it to 90%? So let's go back to second calculate, go to the value, change that to 90, for an x value of 90, and hit enter. We'll notice that it's going to cost $720,000. So let's figure out what the additional cost to the companies would be. So I know that it was costing at 85, it was costing the companies $453,000, we'll just say $333. If I change it to remove 90%, it's $720,000. So as a new lawmaker, I might say, am I really willing to risk, having these companies spend this much money, because then I might not get their vote. So what it's going to cost the company would be, if I subtract these two, it's going to cost these companies, over $250,000 to change the, to remove 5% more emissions from their smokestacks. And again, as a member of Congress or a state legislator, I might not be willing to vote a law into, power, or vote for a law, I should say, if it's going to cost these companies $250,000 to abide by the law. So, we talk a lot of times about, when are we ever going to use this type of information in the real world? Well, here's a problem where you would. Now, probably the state legislator itself is not going to calculate these numbers. He probably has somebody working on his team that's going to do that. But again, you would want to know that you're going to ask a company to pay $250,000 to to apply by this new law. Not something that you should take very something that you should take very serious. Not something that you should just say, yeah, I'll vote for this because it sounds like it's good for the environment, but it's not necessarily great for the companies that have to pay that amount of money.